uncompetitive is parallel because the change of Vmax and Km are changed by same number alpha prime. Because if you look at the Mercatus-Menten equation of the uncompetitive, it is the V naught equals to Vmax over alpha prime times substrate concentration over Km over alpha prime plus substrate concentration. So change of Vmax and Km in the presence of an uncompetitive inhibitor is always changed by the same number alpha prime. That's why it's parallel. And then if you look at the competitive and pure, then this is easy because easy in the sense that you can read off the intercept. This is the same Vmax and Vmax apparent, and then this is moving this direction. This must be no change in Vmax, and then increasing Km because it is moving inside, so it has to be increasing. And then this one, same Km, lower Vmax. So this is something like this that doesn't look like a parallel line, but then in both cases is in decreasing Vmax, decreasing Km, decreasing Vmax, decreasing Km. In this case, it will be a mix. Why? Because changing of Vmax and Km is changing by a different value. The only possibility is that it is the non-competitive, because we know that for the non-competitive, it is the V naught is equals to Vmax over alpha prime times substrate, alpha over alpha prime times Km plus substrate. So the change of Km and Vmax are not the same in non-competitive inhibition. It all depends on the alpha and alpha prime value. And that's why it can be this way or it can be this way, straight line. Okay? So you can draw a straight line any way you want, like this. So, question?
Could you repeat that?
If you can draw a straight line that is higher than this point, and then to the left of this point, like this, or like that, or whichever way, okay? This straight line will satisfy a lower Vmax and lower Km, right? And then the change is different. Why? Because in the case of, let's say, non-competitive inhibition, they are not changing by the same magnitude. That's why.
So you're just saying that if we were like the pictures, it's not always going to be like that slope. It's because the values will vary.
Yes, if the slope is different, just by looking at slope, it's not as informative.
Yeah.
But you have to look at the change of the Vmax and change of Km value. That will be informative.
Okay.
Let me double check, see what else I need to say. Oh, alpha value, right? Alpha value. The best way to look at change in the alpha value is to look at what reversible inhibition first, so you know which mechanism, which Mercatus-Menten equation to use. So for competitive, we know that it is Vmax substrate, alpha Km plus substrate. Non-competitive, I just competitive. The way to look at the change of alpha on a line river plot is that if we see that if alpha is increasing, like we have two different alphas, and alpha is increasing, what does alpha increasing mean? 1 plus I over Ki. If we increase the inhibitor concentration, we're going to increase the alpha. So we can plot the straight line of different concentration of the inhibitor. Then it's going to give you different alpha values. The higher the inhibitor concentration, the higher the alpha value. The higher the alpha value, the bigger the Km in the presence of the inhibitor. Why? Because it's alpha times Km. So we'll see that the competitive one will be moving like this because the Km is getting bigger and bigger. So use the same rationale, you should be able to tell how the movement of the curve when you are having different alpha values. The question is that would increasing the Ki increasing the alpha? I was going to address that because one of the questions that one of the answers, right? Think a little bit about what you just asked. Can you increase or decrease the Ki of this particular inhibitor? Okay, right? So if you look at this equation, the only variable is alpha and inhibitor concentration. Ki is a constant number reflecting how well the inhibitor binds to the E. So indeed, you can only say increase or decrease or difference of Ki to compare two different inhibitors. Then you can say that. So the only way the alpha can change would be changing the inhibitor concentration. So I think I am going to move on, not to show all the possibility of change of alpha value for the different line plot for different inhibition. I think that's another thing that is more useful for you later. So think of it that way. The way you can do it is just looking at the equation, and then you can see that the change of the Km and the Vmax correspondingly. If you change the alpha value or the alpha prime value according to different concentration of the inhibitor. Okay, another thing is this one, if we go through it, is informative. We can look at the enzyme inhibition using the rate of formation and substrate, like this. And then we know that this is the Vmax. So then, if, let's say this is without inhibitor. Okay. If it is a competitive inhibition, that means in the presence of an inhibitor, the rate of product formation will be less, right? So then, let's say we can pick any of the substrate concentration. This will be the rate of product formation of this concentration of substrate. In the presence of an inhibitor, that rate of product formation will be less. So it has to go lower. It cannot be going higher, right? In the presence of an inhibitor, it has to always go lower. Why? Lower than this blue line. Why? Because when you read off the same substrate concentration, this is a lower rate of product formation. By definition, all enzyme inhibition, all enzyme inhibitor, presence of enzyme inhibitor, it will lower the rate of product formation. So always go lower. So it all depends on how the graph goes. If it goes eventually reach Vmax, so that will be competitive. And then if we go and then plateau, that is with another lower Vmax, this is apparent Vmax, then it got to be not competitive. Got to be either the non-competitive or uncompetitive. So that's how you can read off the octaves matrix maintain curve in the presence and absence of an inhibitor. Yes?
For that one, wouldn't the non-competitive same Km, so that it would go according to the blue line, with same Km, and go a little under Tmax.
Okay, so that's a little more tricky to draw on. The one that is a good question. He's asking about the pure non-competitive. They have the same Km but lower Vmax, right? So how would that look like? So I have to first of all indicate the Km value first, right? So then for pure non-competitive, it's more difficult to draw. So this is a graph of no inhibitor. This is the Vmax. Half of the Vmax is here. So if we read off the curve, this is the Km. So then we know that, let's say now we're drawing one that is a pure non-competitive. It has to be lower. The Vmax has to be lower, right? This is a Vmax apparent, has to be lower. And then half of this, let's say, this is the Vmax apparent, let's say. And then half of this is half of the Vmax apparent. And then this Km has to be the same as this one, so it has to go this way. Does this make sense? You just read off the half of the Vmax, and then they have to be the same. Question? Are you following? Yeah.
So on the last year's intern, number 35, it was asking about a straight line equation.
I'll address that. That was question was number 35. Last year midterm question. Can I address that? Let's go through this one. So let me know. I'm going to go through chronologically. If you want me to speed up, yell at me, speed up, so I can skip not that much information. So that's fine. Okay. But this is I think I addressed everything. That was that should be okay. Okay. Go over the difference between pure and mixed inhibition. Good. I just did. So the difference is, remember here, this is the part. The difference is that there are three different scenarios for Ki and Ki prime equal, or one bigger than the other one, or much more than the other one. So pure and mixed, depending on Ki and Ki prime. So this is looking at Ki equals Ki prime, Ki bigger than Ki prime, Ki smaller than Ki prime. And then that will be in terms, we'll give off alpha prime smaller than alpha smaller than alpha prime, alpha bigger than alpha prime. Same thing. And then this is pure. These two are mixed. Number 5 is the example that I used to illustrate a non-competitive inhibition that with the understanding of how the alcohol dehydrogenase works. Because in the discussion of alcohol dehydrogenase, I mentioned about acetaldehyde as the substrate. NADH is the coenzyme. The reaction will require a hydride ion transfer from NADH onto the substrate to form the ethanol product. And naturally, acetaldehyde binds in a different location in the active site than NADH. That's why both of them can coexist in the enzyme active site. So the example I gave was that hypothetically speaking, if binding site of NADH is so different from the binding site of acetaldehyde, so that binding of NADH does not affect the binding of acetaldehyde and vice versa. If that is true, then if there's a NADH analog, a molecule that is binds to the NADH site, then this molecule can bind to the NADH site without affecting the acetaldehyde bind and vice versa. Then it will satisfy the pure non-competitive inhibition. If, let's say, it is not true, binding of acetaldehyde actually change the active site structure of alcohol dehydrogenase somewhat, that binding of NADH is not as well, or vice versa, then that might be a mixed inhibition if that molecule is binding that's affecting the binding of acetaldehyde. Okay. Now, let me clarify that point. I shouldn't use the NADH as an example. I should say binding of the NADH analog to the NADH site, if they somehow change the conformation so that acetaldehyde does not bind as well, or binding the acetaldehyde, the alcohol dehydrogenase active site, change a little bit. Now NADH analog cannot bind to the NADH site as well, then it will be a mixed inhibition. But it's still a non-competitive inhibition because they bind at a separate site. So NADH analog, if it is an inhibitor, this is going to be a non-competitive inhibitor. Depending on if it interferes with acetaldehyde binding or not, then it will be pure or mixed. All the equation for reversible inhibition in terms of the case-Manton equation, we did that, right? So, so that would be those equation that contains alpha and alpha prime. What is the difference between Km and Ks? So we know that in both cases, Km is Es over Es, Ks also E times S over Es. However, the assumption of Km and Ks is different because the assumption is that for the Ks, we are just looking at this one, just looking at the reversible equilibrium aspect of the substrate binding. Whereas for Km, we are looking at the whole thing. Okay? Because of that reason, if we express them in the form of rate constant, the Km is K minus 1, K cat over K1, versus Ks would be just K minus 1 over K1 at equilibrium. So that would be the difference between Km and Ks. So can Km be equal to Ks?
Yes.
Yes. How? Yeah, great.
If K cat is negligible.
When K cat is negligible, that means K cat is a lot smaller than which one? K minus 1. If that is true, then Km equals Ks. Why? Because they are only different by this term. If this term is so much smaller than k minus 1, adding a small term to a big number would be same thing as just that big number. So that would be defined. So what does that mean? Conceptually, that means is that k minus 1 is a lot bigger than k cat. What is k minus 1? K minus 1 is after substrate binds in the enzyme active site, it dissociates out. Is how fast it dissociates from the enzyme active site. Whereas k cat is upon binding, how fast it is to form product, right? So when k minus 1 is a lot bigger than k cat, that means that after it binds in the enzyme active site, it just dissociates. It's not going to form product because k minus 1 is a lot bigger than k cat. So it's a lot faster to dissociate than form product. So then the picture, mental picture would be that with a free enzyme, a substrate, let's say it has a very high k minus, with a k minus 1 a lot bigger than k cat, that would mean that it will bind, just come out like this. It's not going to form product. But once it is equilibrium, once it reaches equilibrium, then one of the times that it is in the active site form product. So that would mean that equilibrium established a lot more quickly. Right after, it's way after equilibrium established, now catalysis occurs. That would give you a Km equals to